Okay? When we talk about forces and we talk about the diagrams, there's a very specific type of diagram that gets drawn when we talk about forces. And so when I refer to the system, I just mean the object that's being manipulated. So the object that's having the forces act on it, we call the system. Okay, and there's a very specific way that we draw motion diagrams for forces that are called free body diagrams. And we'll get to that here in a second, but our system is our object that's being manipulated, okay? Whereas the agent is the cause of the force. System is what's being acted on. The agent is what's doing the acting, okay? Or that's making the force that's causing that motion. So there's really two main types of forces. There's lots of different types, but there's two main kind of umbrella categories of forces. The first of which is a contact force. So just based on its name, what can we imply that a contact force does? Yeah, it makes contact with the object, okay? So pushing, holding, pulling, all of those things are considered contact forces. Okay, I'm in contact with the system. The agent is in contact with the system. That's considered a contact force. So any type of push, pull, even holding, carrying, those types of things are considered forces. Okay. The second type of umbrella force or overall type of force is called a field force. Okay, and field forces are exerted without contact, so they don't have any contact with the object. There should be one type of field force that we are very familiar with or that we can assume. Does anyone know what that is? Magnets, yeah, okay. And gravity was the big one I was thinking of. Magnets, yes. There is a magnetic field which exerts a force. We won't deal with magnets in this class at all, but we will deal with gravity, okay, and the gravitational force. So if I drop my textbook on the floor, is there anything pulling my textbook down physically? There's nothing that comes up from the floor, grabs it, and brings it down, right? But there is a gravitational force that pulls it down. Okay, so we have a gravitational force that's exerted on my book that will start to pull it down. There's no like little arm that comes up out of the floor and pulls it down for me. Okay, it's going to do that itself. As it's falling through the air, what type of acceleration does it have? As my textbook is falling, what type of acceleration does it have? Negative. It has a number. Yeah, negative 9.8. It has gravity. It has acceleration due to gravity as it's falling through the air. So that gravitational force has acceleration due to gravity acting on it as well. Okay. So let's talk about the net force and what's it mean to be a net something. Okay. Hopefully you've heard the term net before, not in terms of a physical net. What's it mean to have a net profit or a net gain? Yeah. Yeah. Everything put together is your total outcome, right, is your net. So that's exactly what you need to think of when we think of net forces. It's the sum of all forces that are acting on an object. The sum of all forces acting on an object. And when we think of net force, we need to also be specific in thinking about directions of our forces. We're going to start with forces just in one dimension, like just horizontal or just vertical, but we're going to get into forces in two dimensions, so things that are moving with angles and all that kind of stuff, where we're going to have to break it into components, which luckily we already know how to do. Okay, but we need to start thinking in terms of net force in the x direction and the y direction. So we always use our coordinate system that we've been using: positive, positive, negative, negative. So when we're finding the net force, if I want to find the net horizontal force, I'm always going to take the positive side forces minus the negative side forces, right? I'm going to take my positives, I'm going to subtract out my negatives. So it's always going to be right minus left for our horizontal forces, and our vertical forces always would be up forces minus down. Okay, and we're going to walk through that once we get into drawing our diagrams, and it's going to become more clear. But I just want you to understand that the direction of the forces does make a difference. Okay, the direction at which they're coming from, which they're going, all that kind of stuff does make a difference. Okay, we're always going to take positive forces minus negative forces to find our net. Okay, does that make sense? Right minus left and up minus down. All right. When an object is at equilibrium, so when it's at rest, or when it's moving at constant velocity, we consider it to be at equilibrium. Okay? An object is at equilibrium when it's resting or when it's moving at constant velocity. Okay, so when an object is at equilibrium, we have to know that our net force, which is labeled F sub net, that's our net force, the sum of the overall forces, is equal to 0 when an object is at equilibrium, so when it's at rest, or when it's moving at constant velocity, our net force is equal to 0. That means all the forces acting on it are canceling each other out. We have equal forces on both sides. Okay, that's what it means to be at equilibrium, is that all these forces are in a balance, they're in a sense of equilibrium. If they're moving at constant velocity, that means they're moving at just enough speed to overcome each of those forces. So if we're moving at constant velocity, we might be moving just with enough force to overcome friction at that constant rate. Okay, that's what we mean when we're saying at equilibrium. So it's important for you to know that the net force at equilibrium and at constant velocity is equal to 0. Okay? So here's a couple examples for calculating net force. And this diagram that you see here, there's 3 different examples. These are examples of free body diagrams. This is what they're called, free body diagrams. And we're going to learn how to draw those and what they mean here in a second. But let's just briefly explain how to calculate net force here. Here's our system, our little black dot in the middle. We have a force that's pulling to the right at 100 newtons and a force that's pulling to the left at 100 newtons, which means our overall net force is 0. Okay, so this system is at equilibrium. We've got equal forces pulling from both sides, so that object is not going to be moving, right? They cancel each other out. Does that make sense? Like, think tug of war here. These forces are pulling in equal but opposite directions, so we're going to have a 0 net force. In our second diagram, both of our forces are pulling to the right with a force of 100 newtons. That means our overall net force would be 200 newtons to the right. So we've got both people pulling to the right. We'd have an overall net force to the right. Okay, and then our final diagram here, this black dot is our system. Can you guys see that okay? Okay. We've got a force of 100 newtons pulling to the right and a force of 200 newtons pulling to the left, which means our net force is 100 newtons to the left. Okay. Here we're always taking right minus left because these are horizontal forces, so we're going to take our positive force minus our negative force. So here we would have either answered negative 100 newtons or 100 newtons to the left. You can indicate it with an arrow with a direction, or you can indicate it with your positive negative. Okay, does that make sense? Okay. When we represent something with an arrow, what's that mean it must be? What type of a value must it be if we represent it with an arrow that are drawn to scale? A what? A vector, right? Forces are vectors. We represent them with arrows, okay? Which is what I just said, okay? Forces are vector quantities. They have to have a magnitude and a direction. Okay, just like what other things do we know are vector quantities? There's 2 other quantities, maybe 3 that we've worked with, 3 actually that we've worked with that are considered vector quantities. What are they? Have to have a magnitude and a direction. Velocity is 1. Displacement, and our third? Acceleration, good. Those are the 3 vector quantities we've worked with so far. Now forces are also vector quantities. Tell me, what's the scalar version of velocity? Speed, good. What's the scalar version of displacement? Distance, good. Okay, is that ringing bells? Hopefully. All right, good. All right, so forces are vector quantities. They have to have magnitude and direction. They're represented by an arrow, which is drawn to scale in the direction of the force. Okay, we need to draw these vectors, these arrows, in the direction of the force. Doesn't matter whether it's a push or a pull. It has to go in the direction that the force is going. and we represented them by an arrow drawn to scale, or as much to scale as we can. Remember, we're talking about kind of a proportionate scale. So we're not getting out a ruler every time to draw it exactly to scale. We're drawing them in proportion to the other vectors. Okay, so if one's 10 and one's 20, we need to make sure that the 20 vector is going to be twice as long as the 10. All right, capital N for our units, which is a Newton. So, speaking of Newton's, we're going to move on to his first law. How many laws does Newton have? 3. Good. We're going to talk about all 3 of them today. Okay. Newton's first law tells us every body continues in its state of rest or uniform speed in a straight line unless acted on by a non-zero force. Okay, so every body continues in its state of rest or uniform speed in a straight line unless acted on by a non-zero force. Book definition first, then kind of normal wording definition, right? Our everyday definition. Bodies at rest tend to stay at rest. Bodies in motion tend to stay at motion. That's, of course, unless it's acted on by a non-zero force. Do we know the nickname for this first law? Okay, the first law is also called the law of inertia. The law of inertia. And what inertia itself actually means is the tendency to resist change. Okay, so these objects that are at rest are going to resist that change. They're going to stay put unless an outside force acts upon them and makes them change. Okay, so inertia is the tendency of an object to resist change. Okay, so objects at rest tend to stay at rest. Objects in motion, basically the difference between mass and what mass looks like to us now in these force calculations. Mass is always considered a quantity of matter, but we can better describe it as a measure of inertia of a body. Okay, the more mass something has, the more likely it is to resist change. Okay, the more likely it is to resist change in motion because it has more mass. Okay, it's harder to move a heavy object than it is to move a light object. Right? It requires more force to move a heavy object. It has more mass, so it's resisting change, okay, or a greater tendency to resist change. Okay, the more matter an object has, the harder it is to change its state of motion, being at rest or in motion. Okay, so we always need our mass to be in kilograms. Even though grams is the base of the metric, right, of our entire system, kilograms is considered our base unit because it's the unit that we deal with the most. We don't deal with grams very much because it's such a small unit. We deal with kilograms. Okay, so how many grams are in a kilogram? 1,000. Good. Okay, there's a difference now between the terms mass and weight. We have to understand the difference between those two terms in our physics classroom now because there is a difference between mass and weight. Okay. Weight's a force, and we're going to talk about the weight force here in just a second, or the gravitational force. But weight is the force of gravity acting on a body, or acting on a matter, a chunk of matter, a chunk of mass. Weight is going to be a measure of how much that force due to gravity is acting on that. Okay, so when you hear people say it weighs less on the moon, does its mass change when it goes to the moon? Does it lose mass particles? No. But the force due to gravity, or the acceleration due to gravity on the moon, is much smaller than it is on the Earth, which therefore reduces its weight. Okay, because weight is a measure of how much the acceleration due to gravity is acting on that object. What's the force due to gravity on that object? Okay, so those are two different things. Weight is always measured in newtons, and mass is always measured in kilograms. Okay, so if the problem tells you this person has a weight of 50 newtons, you know that that's having to do with basically how much gravity is acting on it. That has to do with its weight force, and you can calculate mass from that. We're gonna talk about the weight force here in just a second, or the force due to gravity. Newton's second law. This is the book definition. It's long. Try to condense it a little bit in your own words. Read it through. Try to condense it a little bit. Acceleration object is proportional to the net force acting on it and inversely proportional to its mass. Acceleration's in the direction of the net force. Okay, so here's our description. Here's our equation for Newton's second law. Force equals mass times acceleration. Okay, and here when we talk about force, we're talking about the net force. So the overall sum of forces here is equal to mass times acceleration. A Newton is a kind of combination of these units. So Newton comes from, the term Newton for the unit comes from this law. Net force equals mass times acceleration. The units for mass are kilograms. Acceleration is meters per second squared. Okay, they condensed this unit right here and they called it a Newton. Okay, so 1 kilogram times meters per second squared is considered 1 Newton. So they kind of just condensed this unit right here into a Newton, which is much quicker than writing this whole thing every single time. Okay, but that's what a Newton is. It's a kilogram times meters per second squared. So if your units in your problem don't match these right here, you're in trouble. It's not going to come out in newtons. Your units have to match. So mass always has to be in kilograms. Acceleration has to be in meters per second squared. Okay? So let's try some here. Find the net force needed to accelerate a 1,000 kilogram car at 4.9 meters per second squared. So what force is it going to take to accelerate this car at this certain acceleration? Okay, we are given the mass, so m equals 1,000, a equals 4.9. So we're going to take F net is equal to 1,000 times 4.9, and we get 4,900 newtons. Okay, so it requires a force of 4,900 newtons in order to get our car to accelerate at that speed. Or at that rate, I'm sorry, not that speed. Okay, that seems easy enough, right? Okay, let's take it a little step further now. What's the net force required to bring a 1,500 kilogram car to rest from a speed of 100 kilometers per hour within a distance of 55 meters? Okay, so here are we given our acceleration? No, we're not. Okay, let's go ahead and write down what we're given. What's it tell us if we're bringing a car to rest? What variable does that give us? Final what? Final velocity. Okay, that means our initial velocity, if we're coming from a speed of 100 kilometers per hour, that means V sub O must be 100 kilometers per hour. And that makes 55 what variable? Do we know? D. Oh, sorry, X. Wrong class. Okay, X. Right, that's our displacement in the X direction, which would mean X sub O is equal to 0. So what do these variables start to line up looking like? What equations might we use? Our kinematics equations. I told you we'd use them all the time. Okay, that means in this chapter too. So we need to fix kilometers per hour before we can really start plugging into equations. So if we use our shortcut, we take 100 times 0.2778. I get 27.78 meters per second for my initial velocity. Okay. All right, so now I need to solve for acceleration. Which kinematics equation can I use to solve for acceleration here? One, two, or three? Three. And we're not looking at our projectiles here. We're back to regular kinematics, right? This is moving only in one dimension. So I'm going to use number 3, which is V squared. V sub O squared. 2A delta X. Can you see that or not so much? The blue, is it too hard to read? I'll go back to white. All right, what do we have for our acceleration? Yeah, Matt.
Negative 7.2.
Good. That's what I had. Now, we need to solve for net force. Okay, so we could take F net equals mass times acceleration, right? M times A. And I'm going to have to move up to the top here because I'm running out of room. So F net is equal to 1,500 times negative 7.02. Negative 10,523.6 newtons. So why is our net force negative here? Yeah. Yeah, there's got to be some force that's trying to slow down the car, whether it's a braking force, whether it's a friction force. Yeah.
I didn't get that.
You didn't get this answer. Okay. Tell me what you got.
I got negative 10,530.
Negative 10,530. Okay, is that what everyone else had? Okay, it could be that I just left it plugged into my calculator, stretched out 7.02 something. But yes, that's close enough. Okay. Okay. But the reason that this force is negative, our net force is negative, is because maybe we've let off the brakes, or I'm sorry, we've let off the gas. We're not exerting any force in the positive direction anymore. We might be exerting a force in the negative direction, whether it's a brake, whether it's friction, whether it's something that's slowing us down, but it's opposing the motion of the vehicle, which makes it a negative force. Okay? Okay, and let's talk about Newton's third law. Whenever an object exerts a force on a second object, the second object exerts an equal and opposite force on the first. Okay, so you've probably heard this law before also in the terms equal and opposite reaction. Okay, every reaction has an equal and opposite reaction. That's what's happening here. There's an equal and opposite reaction to every force. That you can label these two forces, whether it's force of object A on object B, okay, or you could just put A, B, or however you want to label it, 1, 2, is equal to the negative force of object B on object A. So whenever I exert a force that on an object, that object's going to exert an equal and opposite direction force back on me. Okay. So if I push that on the table with a force of 10 newtons, the table is going to exert a force of 10 newtons back up in my direction. Okay, so if I'm exerting a downward force, I'm exerting a negative force here on the table. It's exerting a positive force back up on me. Okay, equal and opposite. Any questions on that one? Okay, let's move on and talk about the weight force, or F sub g. When we talk about the weight force, we're looking at how an object's mass is affected by the acceleration due to gravity, or the gravitational force, okay? So if we use Newton's second law, which is what we're going to use here, which is force equals mass times acceleration, we can solve for what we consider the weight force. And the weight force is labeled F sub little g. F sub g, or force due to gravity. That's how I will name it, is force due to gravity. Okay? And we can derive that force using acceleration due to gravity, which is little g. Okay? So here we've got our force due to gravity, or our gravitational force, is equal to mass times acceleration. But acceleration is the acceleration due to gravity, and we label that with a little g. Okay? And we've done that in our projectile equations. We've done that in our kinematics equations. But since our acceleration is due to gravity, we're going to use little g. So when I ask you for the weight of something, I'm asking you for the force due to gravity, or F sub g. Okay? So you might want to put this one down. Weight is equal to the force due to gravity. Okay? And whenever we solve for force due to gravity, we're going to take mass times 9.8. Mass times 9.8. And the reason we don't use negative 9.8 in this case is because we're always going to draw those vectors in the downward direction. Okay, we're always going to indicate with our diagrams that force due to gravity is going in the downward direction. Okay? So both force and acceleration for gravity are downward. So F sub g will always be pointing in the downward direction, which will account for our negative. You can put it on.
Hang time isn't like the peak height, it's just
It's total time.
total time.
Yep. Okay. So here we don't plug in 9.8. We keep it at regular 9.8, and we'll indicate with our direction that it's going in the downward direction. Okay? All right. Let's see. Just a couple more things to get through here. All right. The normal force. When we're talking about something at rest, we already know that its net force is equal to 0. Okay, we know that an object at rest has a net force that's equal to 0. Okay, but if I have any object sitting on a surface, okay, I have this object, my calculator sitting on the table, I have a force due to gravity that's pulling it down, right? Gravity, the acceleration due to gravity is pulling that down. So why isn't it falling? Yeah, there's a surface here that it's sitting on that's applying a force in the equal and the opposite direction, right? That has to go with Newton's third law. There's a force on the table that's pushing up in the equal and opposite direction to keep it at rest. So since it's at rest, we know that those forces have to be equal and opposite because our net force is 0. Okay, so in order for an object to be at rest, we've got to have those forces acting in equal and opposite directions. And there's a name for this force. Okay, so that's what I just talked about. This is called the normal force. Okay, the normal force is the force that's acting upward that's resting on something, resting on a surface. Okay, so anytime I have an object resting on a surface, there's something called the normal force that's restoring its equilibrium. Okay, that's counteracting against gravity. Okay, so the force that the table or the surface is exerting in the upward direction is going to be called the normal force. Okay, and every single object that's sitting on a surface has a normal force acting on it. Every object. If it's hanging in the air, it's not resting on a surface, which means it doesn't have a force being exerted on it from the surface. But anything that's resting on the surface has a normal force acting upon it. Okay, and that's going to be counteracting gravity, so it's always going to be going perpendicular to the surface. Okay, if you open up your textbooks, we're going to take a look at a diagram of normal force. Okay, so on page 88, there's a diagram that looks similar to this. There's those three pictures, I think they're on the left-hand side of page 88, that look like this for the normal force. So I want you to kind of keep these diagrams in mind, but basically there's three different situations here. The first of which the box is sitting at rest. The second of which I'm pulling up with a string with a force of 40 newtons. Second of which I'm pushing down on the object. And all three of those things have different degrees of normal force acting on it. Okay, so let's go ahead and start trying some of these problems with the normal force. Okay, so on page 88, we want to find first the weight of the box, and we want to find the normal force acting on it. Okay, so for this box that's at rest, this box is at rest, that means the net force must be equal to what? 0, okay? So let's walk through basically what's happening in this diagram. Take a look at your diagram. How many forces are acting on that box for the first instance when it's at rest? 2 forces. And are they in the y direction or the x direction? Y, okay? So here, when we calculate net force, remember it's the sum of all forces. So we're going to take our positive forces minus our negative forces. So which of those forces is acting in the upward direction? Which of those forces looks like it's going up? Which one? The normal or the gravitational force? The normal, okay? So we're going to take F sub capital N, that's what we label the normal force. And we're going to subtract out the forces that are acting in the downward direction, which is what force? F sub G. Okay? So here's our net force equation. F net is equal to up forces minus down forces, right? That's the sum of all of our forces here. Up minus down. Okay? And what else do we know about something at equilibrium, that F net is equal to 0? Okay, so if I substitute a 0 right there, that shows me that mathematically my gravitational force is equal to my normal force. Okay, and that makes sense because those two forces should balance each other at equilibrium. Do we agree with that? Can we see that? Okay, good. So now if I want to calculate the normal force, I know how to calculate F sub G. That's all I'm going to do here. Tell me my equation for F sub G, or force due to gravity. M times G, mass times gravity. Okay, so this chapter requires a lot of substitution, a lot of manipulating of equations because multiple things are set equal to multiple other things. Okay, I know that seems kind of vague, but we have to be able to substitute these equations lots of times, okay? So force due to gravity for this object, it says it's a 10 kilogram box, right? Doesn't it tell you that? The box is 10 kilograms? Okay, so that means our F sub G is equal to 98 newtons. And then if we go and substitute that back over here, that means that our normal force is equal to 98 newtons. Okay? Does that make sense? Okay. So that's for an object at rest. Up forces must equal down forces. Object at rest. Okay? Let's take a look now at the second situation. Do we have any questions on this one before we move on? Let's take a look at the second situation really quickly. Find the normal force if I push on the box with a force of 40 newtons. So this might actually be your third one, but it's the push. Okay, so when I push on the box. So here, how many forces do I have acting in the upward direction? Take a look at your diagram. How many arrows do I have going up? One. And what force is it? The normal force. Okay? So that's all my up forces. I've done all of it. Now, what forces do I have going in the downward direction? F sub g, my force due to gravity, and also the force that I applied, okay, or the push force. You can label it either force applied or force sub P for force push or F sub push. Whatever you want to label it is fine, okay? I usually just keep my applied forces, things that I'm applying to it, as labeled APP, okay, applied. So here, is my object moving? Is it being lifted or removed from the table? Okay, so it's still at rest. My object is still at rest, which means my net force is still equal to 0. Okay, are we good with that? Still at 0 there. We're going to have to speed it up just a little bit. My normal force is what I'm solving for. My F sub g, my force due to gravity, does it change for my object? No. My object still weighs 10 kilograms, which means my force due to gravity is still 98 newtons. Sorry, 98. Okay? And what's my applied force in the negative direction? 40 newtons. Because it told me in the problem right here. I applied a force of 40 newtons. Okay, so now I'm going to solve for the normal force by moving both of these terms over to the left side of the equation. I'm going to add both of those over there. And I'm going to get F sub n equal to, what do we get? 138 newtons. Okay, so it's exerting a larger force back up on my hand because I'm pushing harder on it. Okay, can we see that? Why that happens? If I push on it, that table is going to exert a larger force on me because now I'm exerting a force in the downward direction and gravity is exerting a force in the downward direction. Okay? Yeah, makes sense? Okay, let's try the last situation here pretty quickly. I know the bell's about to ring any second. Okay, normal force if I pull upward. We need to pay attention here. If my pull upward, is it removing it from the table or is it just lifting it a little bit? Is it just relieving some of that normal force pressure, as I like to call it? Is it leaving the table? No. Okay,